My name is Savannah Lennon, and this is my lab report 2 for Physics 2211. This lab was focused on the motion of a falling object. This is important for us to study because it's a good example of constant acceleration. That is, assuming the object is in free fall with negligible air resistance. The acceleration acting on objects in this state is the acceleration due to gravity, which is equal to 9.8 meters per second squared. In most cases, however, an object will experience differing amounts of drag depending on its size, shape, and mass. If drag is equal to the weight of the object's mass times the acceleration due to gravity, then the acceleration will be 0 and the object will fall at constant velocity. This was not the case in my situation, as my drag force turned out to be slightly smaller than the weight of my object. Along with the concept of constant acceleration, or lack thereof, it is also important for us to study this because this specific situation helps us see how Newton's second law incorporates multiple different forces and how these forces can change the outcome of motion. I'll talk more on drag later in this presentation, and in my case, I used a crumpled up surgical mask to be my object. Overall, after analyzing its motion, my observations were comparable to the predictions made by my VPython code. The mass of my object was 2 grams, which converted to SI units is 0.002 kilograms. You also see here my initial position and velocity for the model. I calculated both of these using the tracker application. The initial position was simply the x and y coordinates at the first time, 0.067 seconds in tracker. In order to calculate my velocity, I took the first 2 time steps and their corresponding positions and used the velocity formula, the change in position over the change in time, to calculate my velocity, which ended up being negative 0.342 meters per second. Now you see my code with my object's mass, the initial position, velocity, and the variable b. This is the proportionality of the drag coefficient, which changes depending on the mass of the object falling. You also see 2 different graphs. They may look extremely similar. This is because my object was so light, but there is a slight difference in the tail ends of the 2. In the graph with the drag calculated, you see that it has a steeper incline as time goes on, leading it to cover less distance. This displays that different forces in Newton's second law can in fact affect the outcome of the motion of your object. Next, you will see the loop that predicts the motion of my object. First, I changed the time loop so it ends when my tracker data ended, which was 0.633 seconds. Then I went in and updated the code to include Newton's second law in order to calculate for the weight and drag forces acting on my object as it fell. This allowed for proper prediction of the object as it fell. Additionally, the weight force outweighs the drag force, which means that the acceleration is not equal to 0. That can be seen in the graphic on the slide. Next, I plotted my observed data and the predicted data in the same graph to display just how similar they are. In addition to this, I have the predicted model without drag. As you can see, the observed and predicted with drag model start off almost identical, separate a little bit in the middle, and then converge again at the end. This could indicate that my drag force is slightly different than I used. An improvement I could make in this lab would to have a more uniform object with a clearer drag force acting upon it, because due to being a crumpled up mask, the drag force could vary depending on how I drop the object. Additionally, in the graph, you can see how the inclusion of drag does affect the predicted motion of the object, as without the drag, the object would theoretically travel further. Finally, what do these findings imply? Overall, this model depicts how important drag is when calculating the movement of objects. Usually, designers want to minimize drag in order to make their creations more aerodynamic and efficient. But in some cases, you would want to increase drag. One such situation would be that of using a parachute. You would want to have a lot of drag there. Furthermore, what would happen if I threw the mask down rather than dropping it? Ultimately, in this case, it would have more force acting downward and may have observed positions more similar to that than the model with no drag. What if I threw it up first? In this case, the object would still have the same effects as we observed in this lab, save for the initial upward motion, meaning that once the object hits its apex and starts falling back down, we would get similar results.